this is my digital sampling lab slide report. In this lab, we analyze different types of signals, we validate our measurement system using a microphone, and then I conduct an experiment to study how distance affects acoustic and sound wave measurements. I'll walk through each of these sections and highlight the key results in each slide. So on this slide is a summary table of the different signals we analyze in the DAC system. Each track corresponds to a different waveform, as you can see here, and for each we identified the signal type, the main frequency, and any other frequency components that were observed in the power spectrum. For like simple sine waves, we can see a single dominant frequency right here, which is expected because they contain only one main frequency component. For more complex signals like ramp waves, we can see a lot more peaks in the spectrum, and that's represented over here in figure 2, as we can see multiple peaks. For signals like the sum of 3 sine waves right here, we can see multiple distinct peaks, and they correspond to each like contributing frequency, as we can kind of line them up over here. But yeah, overall the table shows how different waveform shapes affect their frequency content. And we can see them based on the graphs that I provided of the power spectrum and the time history, the voltage versus time graphs in figures 1 through 6. So moving on, in this section we validated the microphone and the DAC system by comparing measurements that we took directly from the source of the frequency, like the tone generator, and trying to capture it through the microphone and comparing those. So the table that I have here shows the PSD values for both cases at several input frequencies from 60 to about 8,000 hertz. And the graph on the right shows a relative response, which is pretty much just the ratio of the microphone PSD to the direct like PSD from the source signal. In the graph, we can see that the system consistently identifies the correct frequencies, mostly around the lower to mid frequencies, and then as we go down towards the higher frequencies, we can see a large decrease in the relative response ratio. And this is expected due to like the physical limitations of the microphone and the speaker, probably as well as because of like effects of where I am doing the conducting the experiment, like in the library when there's other background noise going on. But yeah, this step is important because it shows that our system is reliable for specific frequencies. So moving on, in the experiment portion of the lab, I wanted to understand how distance can affect the acoustic signal measurements. And so I was specifically interested in how like signal strength and noise can change as you move the microphone farther away from the speaker. So based on the validation test that I did previously, I chose about a 1,000 hertz for my frequency, and the main question I wanted to answer was how does increasing distance impact the signal amplitude and the measurement quality. And the goal was to quantify how the PSD changes with the distance, and then evaluate how the signal attenuates after that. So for my experiment, this is pretty much the setup, but I played a constant frequency tone through a speaker. I recorded that using a microphone that was connected to the DAC system, which gave me my graphs and data straight into my computer. I kept the speaker volume and the frequency constant to ensure those conditions were stable, and I took measurements at distances from 0, 3, 6, 9, 12, and 15 inches from the speaker of my laptop. At each distance, we recorded the time domain signal, and that was raw data, and then we converted them into the frequency domain using PSD. From this, I extracted the peak frequency and the peak PSD. And then on the next slide, I have my results. So right here, this slide shows the results. As I just mentioned, the table on the right lists the measured peak PSD values at each distance, and the graph shows how the PSD changes as the distance increases. So clearly there's a decreasing trend in signal strength as the distance increases, and this is expected because sound energy it dissipates and spreads out as it travels. So that the amplitude detected by the microphone will will be reduced. At the same time, the background noise is also becoming more noticeable at the larger distance, so the signal to noise ratio will be lowered. One observation that's important is that the dominant frequency is still constant across all the distances, which shows that the frequency isn't affected by distance, only the amplitude. So this confirms like the expected behavior of what I was going for, like the signal attenuation. So in conclusion, this lab showed how different signals appear in the frequency domain using power spectral density. We did confirm that as the signal amplitude decreases, the signal amplitude decreases as the distance increases, the dominant frequency remains constant, and the signal noise ratio decreases at larger distances. Some complications included background noise, some like sound reflections in the room, and maybe some alignments between the microphone and the speaker. Overall, the results matched expected behavior.